Okay, so the previous talk was about Riemannian geometry and differential geometry. This one's going to go to generalized nonlinear geometries, or what are called Spray and FINSLER geometries. And I'm going to discuss what we call geometric fabrics and how those can be used to design behaviors for robotics. So the core of this talk is really about how do we get robots to have sophisticated reactive behaviors using geometries. Oops. So the motivation is really about collaborative robotics. So collaborative robots have to be constantly reactive, do real-time processing, and just adapt to everything that's happening around them. People are moving, things are changing at the speed of physics. And so a lot of the classical algorithms that we do for behavior generation, planning and control, trajectory shaping and stuff like that, they take time, and to get this sort of reactivity, we have to actually take a lot of that stuff and push it into a lower level. And what we do here, kind of the thesis of this entire thing, was you push as much as possible into the underlying geometry of the system, so that it just exists as part of the space, and not only is immediately available, but can also exist independent of task, and so it can be leveraged across many tasks. So here's an example of one of the earlier systems. These are called Riemannian motion policies. It's kind of the initial foray into these areas. What we have now are called geometric fabrics, which is really going to be the crux of this entire presentation. And we'll show some comparisons between them. But this captures, in a number of systems that we've developed, kind of the core ideas. By pushing a lot of the behavior into the underlying geometry of the system, we're able to get very reactive behaviors and program these things, and ultimately learn these things at a much higher level, these sort of behaviors. So here, all of these are using the same sort of underlying behavior generation system, but in different ways. This one is watching the hand and using it to control the fingertips and get human demonstrations from this. And we'll see how we're able to use those actually as imitation learning examples for training geometric fabrics later on. But all of this is made so easy because much of the behavior is just pushed down into that underlying geometry. This is an example of a full end-to-end perception pipeline system. There we go. And here's a collection of a number of the demos that we've put on over the years. All of these are using the same system and the same ideas. And so we've had this behavior generation tools running on a number of robots and a number of tasks. And it really makes programming these things much easier, and especially like reactive and adaptive programming of behaviors, because a lot of the collision avoidance, self-collision avoidance, joint limit avoidance, and all that stuff is just done automatically. So to give a kind of picture of where these ideas sit in the overall robotic system, here's an example of a robotic system that we're developing in NVIDIA called Isaac CORTEX, which takes the tools from Isaac Sim that are built on the Omniverse platform and wraps them up into a reactive robotic system. So a typical robotic system will start with perception, pulling in information to shape the world model. It'll extract logical state from that. Decisions will be made using any of a number of state machines, decision trees, or in this case, what we call decider networks. And those will choose actions. But one thing that's unique about this system is the actions are relatively high level. They aren't joint level commands or anything like that. They're like, where should the end effector go? What direction should it approach that target from? And those actions are sent down to what we call intelligent policies that process those things and actually generate a lot of the behavior that you're seeing. And so these upper levels up here can focus on just reasoning at a higher level and doing that reactively and enabling users to program that themselves. And then all the low-level behavior generation is done by these intelligent policies. And so this entire tutorial is really focused on that last little piece right there, the intelligent policies. And those intelligent policies, in many cases, define joint level trajectories, and those are sent off to control to be executed on the physical robot. Okay, so here's an overview of the tutorial. It's really broken up into 3 parts. The first part focuses on these geometric fabrics, generalizations of Riemannian geometry and such. The next part focuses on the geometry hypothesis, which is something that we're starting to develop, where we really believe that a lot of behavior is compressible into the underlying geometries. And this is starting to show promise as a really important inductive bias for training. And we'll show some initial results there. And then finally, I'll go over some tools for actually designing these things, how to create different spaces that are relevant, define pieces of the geometries in different spaces, and how to transform those all into a combined system that can control the robot. So one quick note, like there's a fair amount of math in these. We do our best to simplify things, and actually these 2 references here, some lecture notes I gave on smooth maps, and a recent paper that we had on nonlinear geometries and FINSLER geometries for robotics. They do a lot of work to simplify the notation and actually make it more based on advanced calculus and stuff like that. But there is still a lot of math. And so like, if you're not following all the math, just I try to give intuition with what I'm saying. So just listen to what I'm saying, try to follow the pictures. I think the intuition will be right there. Okay, so the first part is going to be on geometric fabrics. And we're going to start off with just taking a look at the geometry of energies and show how that leads to a notion of geometry as a paths. And we're going to create a generalization of nonlinear geometry, which just really focuses on the path. The geometry is just the collection of paths that the differential equation represents. And we're going to show how we can take those ideas and then endow that with a notion of energy. So we end up with what we call a fabric for, it's kind of an underlying differential equation that represents a nominal behavior of the system. And that fabric is fundamentally stable in important ways. We'll show some examples of that and derive how we get there. But importantly, this fabric, really, you can just think in your mind of it as like this network, this road network of paths that the robot can follow. So like paths that just automatically avoid obstacles or anticipate joint limits or anticipate self-collisions and stuff like that. And so the policy that's written on top of that just drives across it, just needs to figure out which path to get on and how to follow that and kind of how to tweak the system as it goes. And we'll see some concrete examples of that. Okay. So from a really high level, this is the basic equation that we're going to look at, and I'm just going to break it down really fast. We'll go into some more detail on how to derive this, but here, let's just take a look at this. So it starts off with a geometric fabric equation, which is going to be perturbed by a policy. So these are the terms that I've been using, and there's this geometric fabric is going to be constructed by this piece here, which we call the generator. And the generator has a particular property that is homogeneous of degree 2, which means that it represents paths. And we'll see what that means. But because it represents paths, you can speed up and slow down along the direction of motion, and the system doesn't deviate from that path. So the equation modulates its acceleration in just the right way so that if you speed up and slow down along the direction of motion, it always maintains that same path. And that allows us to regulate speed and actually get this system to conserve energy so that the policy always has this fundamentally stable fabric on which it's driving. And so that's kind of a 1,000-foot view of this thing. The geometry itself is a road network of paths, and the geometric fabric is that geometry with some well-defined measure of conserved energy. And what we'll see is actually that all policies actually operate over some geometry. Sometimes that geometry is useful and sometimes it isn't. But if we design it really well, we can pack a lot of information into that geometry and can be really important for data efficiency or just policy design. So just kind of incrementally stepping forward, these are what I call the major players in geometric fabric design. Just kind of the main concepts that we play with. So one is the geometry of paths, which we just described. Next one is a conserved energy, so that this geometric fabric, which is defined by the geometry of paths, actually conserves that energy and gives this stable geometric fabric over which policy can drive. Then we have the policy, which is actually driving across that, but we also have something called a system metric, which defines how easy or hard it is to push the system from a given path. And as an example of that, and we just saw from the previous talk that Riemannian manifolds have this notion of a Riemannian metric. This is actually the same idea. But in this context, this system metric acts as a priority in sense, defining how easy or difficult it is for some perturbing force from the policy to push the system away from it. So here's an example. What we have on the right here is actually a geometric fabric, which is navigating these three obstacles and trying to get to this point here. The fabric itself has the obstacle avoidance encoded into it. And part of the geometry also funnels the system into here. Later on, I'll have an actual picture of this this geometry, but right now it's kind of combined with a forcing policy. And this forcing policy tries to pull the system toward this point. Right over here, it's difficult, like the system metric defines that it's difficult to push the system away from the path because that would push it into the obstacle. But over here, as another example, the system metric is more loose. And so the policy can push it much more easily and bend the system toward this, this target. So we'll see how that plays in. So in the next few slides, I'm going to define, talk about the geometry of energy. And that's going to lead to this notion of path consistency, which shows us how we can define general geometries of paths, which are called Spurry geometries. Then I'm going to talk about energization of those things, energization in the sense of speeding up and slowing down and along the direction of motion to conserve a particular energy. And that's going to give us the tools to actually construct these geometric fabrics. Okay, so the starting point of this stuff is the calculus of variations. And this is related to what Naomi was talking about, where fundamental to a lot of geometries is the notion of like path length minimization. But the main takeaway here, without going into too much detail, is that we start with what's called a Lagrangian. We'll ultimately pass it through the Euler-Lagrange equation, and we'll get out an equation of motion. And this equation of motion is actually the geodesic equation for how the system moves. In a little bit more detail, this Lagrangian defines a little cost element for this optimization problem, which is the calculus of variation problem. The calculus of variation problem says, if we look at all trajectories between a pair of points, and we measure the cost of those things as this integral, which trajectory is the minimum cost of those? So we're actually optimizing over a set of trajectories, this cost integral right here. And it's well known that that solution or that problem is solved by this Euler-Lagrange equation. So we can write this equation down, and solutions to this Euler-Lagrange equation define critical points of this thing. This is effectively a functional version of setting the gradient to 0, basically. And if we stare at this thing compared to this equation over here, all we're doing is actually writing out this derivative, dt, because L is a function of position and velocity here. And if we do that, we get this form, which is actually very reminiscent of classical mechanics equations of motion. We'll see an example of that in a little bit. But in many cases, I'll write down these systems just in this form right here, which is an equations of motion grouping of the terms for the Euler-Lagrange equation. So here's an example of that. If we take the Lagrangian to be the classic kinetic energy, then we get back the classical equations of motion. This is what's used to model any robotic system, like this Franke that's right here. So fundamental to any Lagrangian and Euler-Lagrange equations is this notion of conservation of energy. And you can show that if you write down the energy as the Hamiltonian of the Lagrangian, which is this expression here, it's a little funny, but we'll see how it simplifies in our special case in just a little bit. But if you write down the Hamiltonian, we can very easily prove that under the equations of motion, this energy is conserved. And in case anybody's interested, I just write it out here. You basically just take the time derivative of this thing, write it out, plug in your equations of motion, you see that things cancel, and you can prove that the Hamiltonian doesn't change. And so if you start with a particular measure of energy, then you'll maintain that energy over time. So all of that was really generic. But to kind of get us to more of a geometric area, we need to add a little bit of structure. And the specific structure that we need to add is this thing we call homogeneous of degree k, or most importantly for us, homogeneous of degree 2. And so just to go through the notation here, homogeneous of degree k just means that if you have a function and you multiply the input by a lambda, the result is the same as multiplying the function by lambda to the k. And so for our Lagrangian case, we say that it's homogeneous of degree 2 if it's homogeneous of degree 2 in the velocity here. So multiply the velocity, scale the velocity by lambda, and it's the same as multiplying the Lagrangian itself by lambda squared. And the kind of amazing thing that happens when you do this is you can show that any Lagrangian that is homogeneous of degree 2, actually more than that, which I mentioned down here, homogeneous of degree k, where k is greater than or equal to 2, has equations of motion that are also homogeneous of degree 2. So if you write out the equations of motion, which is just apply the Euler-Lagrange equation to this, and write it out, you can very easily show that this thing here, the equation of motion, which is related to like this geodesic equation, is homogeneous of degree 2. And it just amounts to some properties. I have them in the slides. You can take a look. We also discuss it in our paper on FINSLER geometry. But that's the main property here. If we add this homogeneous of degree 2 property to the Lagrangian, we get an equation of motion that's homogeneous of degree 2. So the question is, why do we care about that? And it turns out that these homogeneous of degree 2 equations are specifically those which are path consistent. And we see an example of this on the right. So here we have a number of points, and we simulate a homogeneous of degree 2 system at different velocities, and we show like the trajectories of the two different velocities. We see that if you change velocity, it doesn't change the path; it just changes the speed with which you follow that path. And we can see why just by examining kind of a finite difference version of the path. So if we look at a specific path here and look at 3 particular points along that path, I think I forgot to label them, but this is qt minus 1, this is qt, and this is qt plus 1, all spaced by delta t. We can write out what the velocity is and what the acceleration is, just as a little finite difference. And this is kind of a heuristic argument, but it kind of gives insight into the problem. And one thing that you see is the velocity scales with 1 over delta t, but the acceleration scales with 1 over delta t squared. And so that's already related to this feeling of homogeneity, but we can specifically derive the property by if we take the velocity and multiply it by some lambda, that's equivalent to taking the delta t and dividing it by that lambda. And if we use that same delta t for the acceleration, that lambda pops out as a lambda squared right here. So scaling, so in order to stay along the same path, if we scale the velocity by lambda, we have to scale the acceleration by lambda squared. And so essentially a homogeneous of degree 2 differential equation like this, where you scale velocity by lambda and it scales the differential equation by lambda squared, it scales the acceleration in just precisely the right way so that it stays along the same path. And this is a fundamental property of these homogeneous of degree 2 differential equations. And so what we saw from the previous slide was if we take a Lagrangian and say that it's homogeneous of degree 2 and derive its Euler-Lagrange equations, that Euler-Lagrange equation itself is also going to be homogeneous of degree 2, which means it's going to be path invariant. It describes a collection of paths, and we can speed up and slow down along the direction of motion without it deviating from that path. We have a pretty cool animation of this right here. This is just the picture before animated. So we're just seeing the system evolving under 2 different initial speeds, where that initial velocity is always pointing in the same direction, just 2 different speeds, and they always follow the same path. So this really gives us gets us to the tools necessary to talk about the geometry of energy, and we specifically call these Lagrangians that are homogeneous of degree 2 with a couple other properties that I'm not really talking about here, but we can look at the paper for that. But the main property is that the Lagrangian is homogeneous of degree 2, and we call these sort of Lagrangians FINSLER energies. And one of the reasons for that is if we write out the Hamiltonian for it, which is this expression right here, kind of a magic property of homogeneous of degree 2 equations is that this this Hamiltonian expression right here spits back out the Lagrangian itself. And so the Hamiltonian, which is the energy, is the Lagrangian. And you might have seen this if you've ever played with Euler-Lagrange equations and Hamiltonians for classical mechanics. You take that kinetic energy, write out the Hamiltonian for it, and miraculously, it's the kinetic energy itself. And that actually isn't just luck. It's actually a property of the homogeneity of the Lagrangian. And so if we have a Lagrangian that's homogeneous of degree 2, its energy is going to be the Lagrangian itself. So we call it FINSLER energy, this Lagrangian here. And it creates an equation of motion which are path consistent, which means that we can speed up and slow down along the direction of motion. It always follows the same path. And this last term right here is what we mean by speeding up and slowing down along the direction of motion. We can choose alpha to be any smoothly varying thing, and it'll always follow those same paths. And importantly, the fundamental collection of paths that are represented by that are what we call the FINSLER geometry. I'm going to go pretty fast through this one because it's not as important for actually constructing geometries, but it's interesting and insightful. And it's related to what Naomi was saying about how the energy relates to the length element. It turns out that, so we've been talking about energies here, which are homogeneous of degree 2. We can square root that and get something that's homogeneous of degree 1. And if we look at the Euler-Lagrange, the calculus of variations problem right here, we can see from the calculus of variations problem itself and just the HD1 property, this homogeneous of degree 1 property, that these values of the integrals are actually independent of speed. And I just write it out here, but the high level is simply that if you change your speed along any given trajectory, this integral will evaluate the same as it was before. So the calculus of variations problem itself is independent of speed along the trajectories. And so it must be that the solution to it is actually something that describes paths and not specific trajectories. And what you can show is if you derive the Euler-Lagrange equation for this form, the square root of the energy, it represents, or it gives you an equation which actually characterizes the full geometry of the system. And the geometry is the same geometry as represented by the paths that are created by the FINSLER energy. So it's kind of an interconnection between length elements and energies. The cool thing about length elements is you can look at it literally as like measuring the length of this path. But specifically, the length element, how you measure that length, can vary depending on the directionality of the system. So here, if you have an obstacle, for instance, right here, if your system is moving toward the obstacle, that might be measured as longer than a system moving away from it. And that's what FINSLER geometry gives you. One important example of a FINSLER geometry is actually Riemannian geometry. So if we take these ideas and say that our homogeneous of degree 2 energy, FINSLER energy, is actually kinetic energy, which is this classical expression right here, then the equation of motions that are derived and the corresponding set of paths that are represented are actually just the Riemannian geometry paths. And then this length element that I mentioned is the Riemannian length element, which is the square root of this thing here. And so that's a kind of fundamental relationship between FINSLER geometry and Riemannian geometry. Riemannian geometry is a form of FINSLER geometry. FINSLER geometry kind of sits as a superset of that. It also emphasizes the connection between classical mechanical systems and Riemannian geometries. This thing we've been describing of the geometry of energy is actually a generalization of this connection between classical mechanical systems and Riemannian geometries. And that connection is really that mechanical systems are Riemannian geometries and vice versa. And that really, like, if you imagine a system, you can have like a bunch of interconnected links and stuff like that, just kind of floating in space, moving and tumbling and stuff like that. That inertial system, if it isn't acted on by external forces, will follow some path. And the miraculous thing is that if you take that same system and start it from the same configuration in moving the same velocity, or same direction, but at a different speed, it'll tumble maybe faster or something like that, but it'll still follow exactly the same path as it did before. That's a property of mechanical systems that isn't really discussed very much, but it's apparent from this connection between classical mechanics and Riemannian geometries. Okay, so that was a lot of construction. But one question is, what type of geometry do we actually need for behavioral design? And I'm not going to go too much into detail about this, but what we see if we really examine these systems is that these metrics here, especially when a bunch of pieces are combined, which I'll talk about a little bit later, act as priorities for the system. And the behavior is really defined by this portion over here. And so if we look at something like obstacle avoidance, which might be a behavior we want to describe, we can ask what kind of priority do we want that behavior to have? And that priority is non-obvious. Well, it makes sense, but there's kind of some cases here. So if a point is close to the obstacle and moving toward it, the priority of this obstacle avoidance thing should be high. If it's still moving toward it, but a little bit further away, it really cares a little bit less about the obstacle, but it still cares about it. But if we're moving away from the obstacle, even if we're close, we actually don't really care about the obstacle. We want to turn it off. And so we want this priority to be a function of both position and velocity. And so these Riemannian geometries, which have metrics that are a function of just position, can't actually really describe those priorities in the right way. So we have to at least go to FINSLER geometry, which allow us to have metrics that are functions of both position and velocity. The issue with just FINSLER geometries by themselves is that this behavioral component, though, is intrinsically linked to the metric itself. And so if we spend all of our representational power defining a metric which represents a good priority, it actually defines for us the behavior, which might not be the behavior we want. And if we do the vice versa and actually design our FINSLER system so that the behavior is right, we don't necessarily get the right metric from it. And so at a high level, we just need more general geometries than that. And so this leads us actually to geometric fabrics. Rather than just using Riemannian geometries or just using the superset of FINSLER geometries, we have to go beyond that to entirely general geometries of paths. And these are actually called spray geometries. So we want to design behaviors using arbitrary homogeneous of degree 2 differential equations where we can actually shape the paths to be whatever we want. And then we take those systems and use this redundancy of speed, the speed redundancy, so to accelerate along the direction of motion in just the right way so that we conserve a specific notion of FINSLER energy. And so this transformation that we go through, we start with a homogeneous of degree 2 differential equation, and then we do this speeding up and slowing down to conserve an energy, which has a particular formula that we can use for it. That operation is called energization. And once we've energized a geometry, this is what we call a geometric fabric. And this here is really just showing, I'm not going to go into detail, but it's showing that we can view these geometric fabrics as actually taking the FINSLER geometry itself, which is the geometry of that energy, and bending it using a zero work modification term to align with the geometry that we want. Okay, so that gives us the basic tools for understanding what fabrics and geometric fabrics are. And kind of at a high level, what a fabric is, actually the definition of a fabric is that it's a conservative, autonomous second order differential equation. And so it's just those differential equations of the form that I was describing, but specifically it's conservative. It has some notion of energy that's being conserved. And we can construct one of those by starting with a generator equation, just some equation that really defines the behavior, and energizing it using the energization operation that I described. And specifically, if that generator equation is homogeneous of degree 2, then that equation describes a collection of paths, and the energization operation does, all it does is endow it with a measure of energy. And that gives us a geometric fabric. So the construction of a geometric fabric is start with a homogeneous of degree 2 generating equation, choose an energy that we care about, energize that system, and the resulting system is this, which is fundamentally stable. So it's fundamentally stable in the sense that we can add to it driving policies that drive across that network, that road network of paths. And that policy will add energy to the system, kind of increase the energy as it kind of accelerates forward and stuff like that. But at any point, that policy can actually stop by just stopping what it's doing and putting on the brakes. And because the fabric itself is conservative, you can show that putting on the brakes in that way will just bleed off energy and the system will ultimately come to rest. And so fabrics constitute fundamentally stable mediums for policies to operate on. And we can encode important behavioral elements into the fabrics themselves. An important property of fabrics are that they're unbiased in the sense that they can't push a system from rest. And that really comes from its conservative properties. So if it has zero velocity, then it has zero energy. And because it's conservative, it doesn't want to move from there. But what that means is that convergence of a system that's forcing a fabric implies that it converges to a zero set of a biased forcing term. So if we imagine like a forcing term kind of pushing on this fabric in different areas and stuff like that, there's going to be points where that push is zero. If that total system converges, it can't converge to a point where that forcing system is actually trying to push it, because it'll just not converge there. And so if the system does converge, then it's guaranteed to converge to the zero set of that. And we have an example of that here. So this is the system that I was showing earlier on, but up here, we actually see the geometry itself. Here we just shoot off a bunch of paths in all different directions. We have obstacle avoidance and we have some attraction to this point here. And so we see that the paths just kind of loop around this area over here. If we then force the system using a forcing term that coaxes the system toward this point, and we regulate energy by bleeding it off in the right way as we get close to that point, we can get the system to converge, and we're guaranteed that when it converges to the zero set of that forcing term, which is the target right here. Okay, this is just a little bit more detail on driving policies. Given the time, I'm going to skip past it pretty quickly, but the main takeaway is any policy can be decomposed into two parts. One part is what we call an energy regulator, which just speeds up or slows down the system. And the other part is a steering term, which bends the system without actually changing the energy. And that gives us insight into the operations of forcing terms on fabrics, which can help us design parameterizations for training systems and stuff. Any forcing policy is going to decompose in that way. And so we can kind of understand the role of that. Let's take a step forward. Here's an example of a geometric fabric system that navigates this logistics-like cubby environment here. The goal is to just move between random cubbies. And all of the behavior is really pushed into the geometry itself. We designed this geometry by hand using some navigation heuristics that were relatively easy to write down. And then we perturbed it with a very simple forcing function. We're able to get this global navigation pretty easily. And this is an example of really kind of taking a problem and pushing as much behavior into the underlying geometry as possible so that the actual policy ends up being really easy. Okay. Given the time, I'm going to go over the geometry hypothesis here, but I'm going to probably skip over a lot of the tools that we have. We'll have these slides online afterwards, and a lot of this information is in some of the papers that we have. But I think this here is pretty important. So let me go into it. So one fundamental property is that there's an underlying geometry to any control policy we look at. We can look at like different versions of control, like standard control techniques like torque control, inverse dynamics control, operational space control, and actually look at what the corresponding geometry is. So torque control is placing torques directly on the physical system. So the underlying geometry is actually the geometry of the mechanical system itself, which has its own inertias and stuff like that, which usually in terms of like a specific policy or a task is not too useful for that task. And so the policy needs to usually do a lot of work to invert at least the important portions of that geometry. And so in many cases, we actually invert that in an underlying controller using inverse dynamics to basically take that mechanical systems geometry and wipe it out and just give us a Euclidean geometry in C space. And so that's good for like trajectory following and stuff like that. But in terms of the tasks, it's not really informative for the task at hand. And so what many people often use is this notion of operational space control, which not only wipes out the geometry, but it replaces it with a geometry that's actually relevant to a lot of tasks. So the natural geometry of operational space control is actually straight line motion of the end effector. And a lot of tasks can use that geometry to, just move the robot in the right way, and it just needs to perturb the system away from it. So we're seeing more and more the use of operational space control as a good inductive bias or starting point for different imitation learning or reinforcement learning techniques and stuff like that, and significantly improve the data efficiency. But what we are trying to do is go one step beyond that. So instead of just doing straight line in end effector space, we're trying to pack as much information down into the underlying geometry as possible. And if we do that, we make it much easier to program these problems or even optimize solutions. So what you see along the bottom here is a very simple CMA optimizer doing some global navigation on top of these geometries just by choosing a single waypoint. So by packing a bunch of information into the underlying behavior, the optimization itself actually becomes really easy. So that gets us to our geometry hypothesis, which is really the statement of saying, from our experience and what we've been seeing in our experiments and stuff like that, it seems like much of efficient behavior is innately geometric in nature, in the sense that it can be highly compressed into an underlying geometric fabric. And some of these things are obvious in the sense of there's a lot of tasks that you can see as geometric, like obstacle avoidance. Those are actually often described as paths using planners and stuff, or opening and closing drawers, turning a valve, things that are kinematically constrained. Even pushing an object or moving an object in forced closure, quasi-static manipulation. All of these have the principle or the property that if we take a solution and we speed it up or slow it down, we consider it to be the same solution. And so those are kind of fundamentally geometric. And we can also kind of move beyond those kinematic tasks and ask like what dynamic problems might be geometric. And this is something we're still currently studying. But it's kind of spurred by this notion of early versions of this stuff, kind of an area called energy shaping. One of the early, or the first application really, was actually to design a cart pole balancing system. And it described that as a classical mechanical kinetic energy, which we know is a Riemannian geometry. And so these dynamic problems in many ways seem to be amenable to these geometric representations. And you can imagine like limit cycles and central pattern generators benefiting from geometric representations as well. And so it seems like a lot can be actually encoded into geometries. And if we do that, we can do things like imagine obstacle avoidance just being part of the geometry of the environment. So any robot that comes into the space can get access to that information immediately. And kind of anything that tries to train or act within that space just kind of has a better starting point, a better prior for learning the behavior or optimizing the behavior. So here's an example of one of the things that we're doing. This is something we call neurogeometric fabrics, where we try to do imitation learning from human demonstration. And the human demonstrations, there's only a handful of these things. We're able to generate, I think, 60 to 80 trajectories for each one. We're able to study the data efficiencies of different models for learning from this data, like both how successful the resulting policies were in terms of like actually being able to successfully complete the task, and how that changed as the number of demonstrations change. And what we find is that in all of these examples, so we're picking up a box in one, we're pushing a coffee can while avoiding it. So we actually have to touch the target first and move around the object, push the object to the target, or extracting a tool tray from this thing, all generalizing to like different orientations of the objects and stuff like that. Neurogeometric fabrics, which encode this inductive bias of paths into the system, significantly outperform the other ones in terms of data efficiency. So we see that in terms of the imitation error as the number of demonstrations increases, the success rate of these things, and performance across all the tasks. And one kind of important comparison is this RMP versus neurogeometric fabrics. Those two policy representations are exactly the same in this thing. The only difference is that the NGF included the geometric bias. And we see that the data efficiency is significantly improved just by including that inductive bias. And we basically, because these tasks are naturally geometric, we effectively get data efficiency for free because we're actually just writing down a model class which is more representative of the problem than it was before. And so we maintain the flexibility of neural policy training while also getting significantly better data efficiency. So here's just a video of some of this at work. Here's some demonstrations of, or some examples of the demonstrations, and here's the deployed policy. In all cases, we gave the system 2 attempts to pick up the things. This here is the neurogeometric fabrics work. The one that I'm particularly excited about is this coffee can thing, which is able to learn to not only push the system, but also do obstacle avoidance of this thing, and with relatively small, kind of practically sized data sets. And if I skip forward, we can see some of the baselines, and each one of these just has difficulties in various ways, just because of the limited data regime. Okay, let's see. Yeah, time-wise, I think I should wrap up here. These just go over some of the basic tools, talk about a practical example of the set of tasks that we can do. Like in constructing these geometries, we often define a whole bunch of different tasks that are all related through this transform tree. And we can populate pieces of the differential equation in different spaces, and I'll pull them all back into the root. And that's some pretty cool, useful tools there. And here we just give the overall system equation for how these things work. I want to move past these. To here, giving an example of geometric fabrics versus RMPs, like what happens if you describe things in terms of geometries versus just describe things a little bit more ad hoc, which is what Riemannian motion policies were. These Riemannian motion policies are what we used in a lot of the systems that we showed earlier. It's actually a very robust code base, kind of hardened and tried. But these geometric fabrics are just performing significantly better in terms of navigation and moving. And we can accelerate along the direction of motion and maintain speed in ways we couldn't with the other tools. Okay, let me just skip this. This is about constraints. And yeah, that's basically all I wanted to go over. The high level really is that a lot of behavior can and should be written directly into the underlying geometry. Because this ends up being task independent. We get both good inductive bias and the ability to share a lot of that prior information with multiple robots, multiple tasks, and all that stuff. And the reasoning behind that, if we kind of open the hood and examine what's going on, is that the geometry defines this road network of paths that the policy can just choose to follow and then learn to navigate across. And this road network of paths is fundamentally stable. And so the system can just drive across it and gain all that information for free, effectively. Okay, and that's it. Thanks. Are there any questions?
Thank you, Nathan. It was a very insightful talk. Thank you very much also for joining us from Seattle. Do we have questions from the audience? Yes, please.
Hello, my name is Stefan Stramijoli. Thanks a lot for a very nice talk.
Nathan, can you hear us?
Can you hear it?
I can hear.
Okay,
great. So I'm very familiar with Riemann geometry and non-FINSLER geometry, and I was wondering, because in the equation you show, it's not very clear. If you take the let's say the Riemann tensor function of the velocity, you have to lift the system, geometrically speaking. Could you say something about it? Because it seems to me that you need that in order to have this effect of velocity dependency from obstacles toward or versus the obstacle. What is the geometry? Are you basically lifting the system to the tangent bundle? What could you say something more about that?
Yeah, it's derived more directly from the calculus of variations. So there's a lot of machinery going on with connections and other things. We ended up deriving a lot of these tools from more of a classical mechanics standpoint, or not classical mechanics, but advanced calculus standpoint. So we have a paper on FINSLER geometry and a bunch of the derivations and this representation of paths, which it's complete in the sense of like all the results that we use and stuff are derived from first principles, but it doesn't go into a lot of the details of vertical spaces and lifting and stuff like that, which gets pretty hairy. A lot of that stuff, especially around covariance and things like that, is actually handled implicitly by the transform tree tools that we use, because the transform trees define how systems pull back from the codomain of a different back to its domain. We define those transformations as fundamentally covariant, and show that it also has a relation to least squares and stuff like that.
But you need to lift it, right? Because you cannot otherwise define a geometry in that way. If you need to define a metric depending on the q dot as well, right? Is that right what I'm saying? Because I otherwise I cannot see how you do it. Either you generalize the action of the Lagrangian and you do a variationals, but then I miss the geometry which is behind it. You lift it to the tangent bundle, right? And then define a metric space there, something like that?
Let's talk about this offline. We can go through the details of specifically how we derive those things.
Okay.
I acknowledge that there's a lot of machinery that makes it very complicated, like in spray geometry and FINSLER geometry, kind of like the fundamental mathematics and stuff like that. But we've derived a bunch of practical tools for being able to leverage that stuff from first principles in these papers and stuff.
Thank you very much.
And yeah.
Nice talk. Thanks.
Do we have any further questions for Nathan from the audience? Not sure if from Zoom. Let's see if somebody wants to speak up. Okay, we have one here from the in-person audience. Go ahead.
Hey, my name is Travers Rhodes. I was wondering, for the energy that you're defining, you mentioned there are a bunch of ways you can generate the energy from obstacle avoidance or how these are related to paths. I was wondering, is there also going to be a connection to the actual energy of the system, that you sort of, these paths that it wants to take are going to be ones that are energy minimizing, that they're easy for the robot to perform?
Yeah, you can combine the classical mechanics of the system with the behavioral dynamics of the system, and actually just add those two together and get something that kind of trades off between those two. And you can also use that to model like floating base robots and stuff like that. And it all depends on how important those elements are to modeling the thing. What we often do in practice is, let's see, I'm trying to remember back to the systems. Yeah, we ultimately just take quantities that are correlated with like inertia and the swing of the arm and stuff like that, and add them as like other differential equation components. So we just add them to the behavioral components so that they just trade off with the desires. And so when it becomes important to disrespect that, so like if there's inertias and stuff like that, which are nice to have or something, but it gets close to an obstacle, then those behavioral components for the obstacle avoidance will just take over because they'll have really high priority. But in areas where it's just kind of moving in free space, they'll just have much more relaxed motion.
Awesome, thank you.